In this video, we're going to show that for any positive integer n, if we start multiplying 4 minus 2 over 1 by 4 minus 2 over 2, all the way up to 4 minus 2 over n, the product is always an integer. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. To look for some intuition to solve this problem, to show that the product is indeed an integer, I'm going to start by trying a few small numbers. So for example, when n equals 1, then it's just 4 minus 2 over 1, and that's 2, so it's an integer. If n is 2, then we start from the number 2 at the above, multiply by 4 minus 2 over 2, which is 3, so 2 times 3 is 6, still an integer. But now when n equals 3, the fraction is no longer an integer, 4 minus 2 over 3. But fortunately, what we've got about is 6. So 6 times 4 minus 2 over 3, and that's 10 over 3 multiplied by 6. So that's 20. Again, an integer. Well, for n equals 4, it's the number above times 4 minus 2 over 4. And that's 70. So this can go on, and we'll still get an integer. But why? Generally speaking, we can actually rewrite the product as multiplying from, say, m equals 1 up to n of the expression 4 minus 2 over m. And I can simplify the expression inside the product. And that's 4m minus 2 over m. Or we can take a common factor at the numerator, and we have 2 times 2m minus 1. So then we can multiply separately. For the 2's, there are n of them. So multiplying, we have 2 to the power n, and then we have the product of 2n minus 1. And in fact, we're multiplying all the odd numbers. While for the bottom, we're multiplying from 1, 2, 3 all the way up to n. So if we want to write it in a shorter form, it's actually n factorial. Now here comes the trick. I'm going to multiply both the top and the bottom by n factorial. Like this. Then for these two terms, 2 to the power n and n factorial, I'm going to regroup them in this way. So there are n 2's, and I'm going to arrange n factorial's components in this way. 1, 2, 3, 4, all the way up to n, multiplying each of them separately. And so I have 2, 4, 6, 8, all the way up to 2n. And in fact, I'm multiplying the first n numbers all together. So on one hand, I have all the odd numbers, and on the other hand, I have all the even numbers. While for the bottom, I have n factorial squared. And so actually for the expression above, we can combine them. The first n odd numbers and the first n even numbers combined together is just the first two n numbers. And you multiply them all together, the result will be 2n factorial over n factorial times n factorial. Now, the reason that this number is an integer, because I can write this as 2n choose n. The number of combinations to choose n objects among two n objects. So for example, when n equals 1, then it's supposed to be 2c1. And if we look back at the top, it's indeed 2c1 is 2. Now for n equals 2 is 4c2. And that's really 6. For n equals 3 is 6 choose 3. So it's really 20, and so on. So from this, we have proved that no matter what a positive integer value n takes, the product of these terms, of these n terms, must be an integer. So this completes our proof. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.